Welcome back to Kinetics. In part 3 of our video, we're going to be talking about the experimental determination of reaction rate. I have separated this into 3A and 3B because I think it's going to get a little bit long. So we'll see how long it gets. Let's go! So, first of all, experimental determination of reaction rates. To obtain the rate of a reaction, you must determine the concentration of a reactant or a product during the course of a reaction. So we're going to have to look at how the concentration of a reactant changes or how the concentration of a product changes. One method for slow reactions is to withdraw samples from the vessel at various times and analyze them. More convenient are techniques that continuously monitor the progress of a reaction based on some physical property, such as the reaction will change color as reactants turn to products, so we can use Beer's law in absorbance to measure the concentration change as the color changes. Experimentally, it's been found that the rate of a reaction depends on the concentration of certain reactants as well as catalysts. Let's look at the reaction of nitrogen dioxide with fluorine to give nitrile fluoride. The rate of this reaction has been observed to be proportional to the concentration of nitrogen dioxide. And when the concentration of nitrogen dioxide is doubled, the reaction rate doubles. So the whole reaction goes twice as fast when NO2 is doubled, the reaction goes twice as fast. But the rate is also proportional to the concentration of fluorine. So if we were to double fluorine, we're also going to double how quickly the reaction happens, say how quickly the product is produced. Even though there's only a 1 in front of the fluorine and there's a 2 in front of the NO, doubling either one of them will make the product form twice as quickly. And so that seems kind of weird. We need a mathematical expression to relate the rate of a reaction to the concentrations of the reactants. So in this case, we're going to say the rate of the reaction is how quickly the product is produced. So the NO2F can be produced at 3 moles per second, or how quickly we can make it to 5 moles per second, or 7 moles per second. And if we double the NO2, or if we double the F2, that NO2F is being produced twice as quickly, even though there's a 2 here and there's a 1 there. So we need a rate law. This is a rate law. It is the rate of a reaction with a rate constant called K, and then the concentrations of the reactants. The rate law has concentrations of reactants only, never concentration of products. And K is a proportionality constant in the relationship between rate and concentrations. It's what makes it work. So as a more general example, we're going to consider the reactions of A and B to give D and E. So we have A moles of A and B moles of B with a catalyst to produce D moles of D and E moles of E. So the rate law is going to have the reactants only and also possibly the catalyst and never going to have the products. So we have rate is equal to K, and A is one of my reactants raised to the power of M. What's significant about M is that it is not the lowercase letter A, which means M is nothing to do with the coefficient in front of A in the balanced equation. This and that are not the same thing. Then we have B raised to the power of N. Notice that N is not the same thing as little b. And C raised to the power of P. So it's not necessarily based on the stoichiometry of the reaction, the rate that the entire reaction happens. The reaction order with respect to a given reactant species equals the exponent. Reaction order equals the exponent of the concentration of that species in the rate law, as determined experimentally. The overall order of a reaction equals the sum of the orders of the reacting species in the rate law. So consider the reaction of nitric oxide with hydrogen according to the following equation. The experimentally determined rate law is rate equals K, that's a proportionality constant, NO squared times H2 to the first power. Notice that in the balanced equation, NO has a 2 and H2 also has a 2. And the 2 in the H2 there is not the same thing as the exponent on H2. So the order of the reaction is second order in NO because this is a 2. And first order in H2 because this is a 1. First order means double concentration, double rate. First order means double concentration, double rate. Second order means double concentration. Quadruple rate. Zero order, which is something that exists, means if you double the concentration, the rate doesn't change at all. So the reaction order is the exponent that you would have to take the concentration change to equal the rate change. Let's look at a couple of examples. Here's our first example. Hydrogen peroxide decomposes in the presence of iodide. This is a catalyst. And this following reaction, we're going to determine the rate law, the order of the reaction, and the value of the rate constant. So let's see what this all means. There was some researcher, who did 4 separate experiments. In experiment 1, he made the concentration of H2O2, the only reactant, 0.1 molar. And then he measured that the rate of the reaction in molarity per minute was 1.01 times 10 to the negative third. In the second experiment, he doubled the concentration and noted that the rate doubled. In the third experiment, he went up to a 0.4 molar and noted the new rate, and in the fourth experiment, he went up to a 0.6 molar and noted the new rate, which makes the H2O2 the independent variable. This is what the researcher has control over, and then the rate will be the dependent variable. This is what the researcher is measuring after changing the concentration. So, when this researcher doubled the concentration, he went the concentration up times 2. He noted that the rate also doubled. So, the rate law is always in the form rate equals K times the reactants. But the reactants are frequently raised to some exponent or some power. That exponent has to be equal to the rate change. So what exponent does this concentration change have to equal the rate change? So 2 to the what power is equal to 2? 2 to the blank equals 2. Hopefully you're filling that blank in 2 as a 1, which means 2 to the first power is 2, or H2O2 to the 1. So that H2O2 is the first order reaction. It's first order because doubling the concentration doubles the rate. You would have to take the concentration change to the first power to equal the rate change. So then the last thing that's left is determining K. Now that I have a rate law, I can plug that in to find K. So it says rate is equal to K times H2O2 to the first power. Let's say I'm going to use experiment 1. 1.01 times 10 to the negative third molarity per minute is K times 0.1 molarity. So I'm going to divide both sides by 0.1 molarity. And notice that I cancel there, and I cancel one of the molarities. And I'm left with per minute. 1.01 times 10 to the negative 3 divided by 0.1 is equal to 0.0101 per minute, or minute to the negative 1. Let's look at another one. At 325 degrees C, NO2 reacts with CO to yield NO and CO2. It's observed that this reaction rate does not depend on the concentration of CO. So we are going to completely ignore CO as if it didn't exist. And so the reaction rate law does not involve CO. The rate does depend on NO, however, and the following data is obtained. So some experimenter, some researcher did this experiment 4 separate times. In experiment 1, they made the concentration of NO2 0.15. In experiment 2, they changed it to 0.3. In experiment 3, they changed it to 0.6. In experiment 4, they changed it to 0.9. And in each of these cases, they watched how the rate changed. So we're going to find the rate law. How does the concentration change equal the rate change? And it doesn't matter which experiments you pick. You can pick 1 and 2, or 2 and 3, or 3 and 4, or 1 and 5. It doesn't really matter. I'm just going to pick 2 and 3, because why not? From 0.3 to 0.6, I noticed that they doubled the concentration. So what happened to the rate when the concentration doubled? So I noticed that it was doubled because I did 0.6 divided by 0.3, and that's equal to 2. So let me look at 1.8 times 10 to the negative 1 divided by 4.5 times 10 to the negative 2, and it turns out that that's equal to 4, which means, let me erase this, get it out of my way, which means that the rate went up times 4 when the concentration went up times 2. So what power would we have to raise the concentration change by to equal the rate change? 2 to the what power is equal to 4? Hopefully you're filling in that blank with a 2. 2 squared is equal to 4, which means that this is a second order reaction. So the rate law is rate equals K times NO2 squared. And we're leaving out the CO because it's not involved. So there's my rate law. Rate laws always start with the word rate equals K and then the concentration of the reactants. Now they want us to solve for the value of the rate constant, so I'm just going to pick an experiment, and it doesn't matter which experiment, any experiment I feel like, I'm going to pick experiment 4. Why not? The rate there is 0.4, that's 4 times 10 to the negative 1, is equal to K. I'm solving for that. Oh my goodness, I forgot a unit. This is horrible. 0.4 molarity per second is equal to K, which is I'm solving for. NO2 is 0.9. 0.9 molar squared, not squared molar. So when I divide by 0.9 molar squared, I'm dividing by 0.81 molar squared. I'm squaring the number and the unit. That should cancel on the right hand side, and on the left hand side that's going to cancel one of the molarities. So 0.4 divided by 0.81, K is equal to 0.49, and then the unit is going to be m negative 1 seconds negative 1. Because molarity, there's still one molarity left on the bottom, and there's also a seconds left on the bottom. Alright, next one. Sucrose decomposes in an aqueous solution into a mixture of two sugars, glucose and fructose. The observed initial rates of decomposition of sucrose at two different initial sucrose concentrations are listed below. So we have two experiments here. Notice this time they put the concentration on the right-hand side and the rate on the left-hand side. That doesn't really matter, that's just how they display the data. So we're going to find the dependence of the reaction rate on the concentration of sucrose, or the order of the reaction, and the rate constant. I want you to do this one on your own. Pause your video now. Alright, so hopefully you paused your video, and hopefully you noticed that sucrose was doubled. It went up times 2. When sucrose doubled, the rate also doubled. It went up times 2. So 2 to the power of what is equal to 2? Hopefully you went 1. 2 to the power of 1. So the rate law is rate is equal to K times sucrose, or C12H22O11, to the power of 1. It's first order. The dependence of the reaction rate on the concentration of sucrose is when sucrose doubles, the rate also doubles. So now we're going to solve for K. The rate, it doesn't really matter which one you pick. I'm going to take the first one. 0.00855 is the rate, molarity per seconds. K times 0.1 molarity to the first. Divide both sides by 0.1 molarity. And we cancel this here, we cancel that there, we cancel a molarity there, and we end up with K is equal to 0.0855 seconds negative 1. If that unit reminds you too much of pre-cal, you can abbreviate seconds with a plain S instead of an SEC, if you'd like. Alright, that ends it for right now. There's a couple more examples on rate law experimental determination, so join me again for our next video.